Hello everyone, my name is Xiao Linfeng, and with me today is Yang Dalin, and we will presenting on this topic, the tragedy of Bluetooth low energy. And we both come from Xiaomi security team, and we are dedicated to researching advanced security technologies and developing automated platforms and conducting security assessment and protection for smart device. And our team members have participated in events like GeekPong, Tianfu Cup, and Butian Cup, and we won Grantley prize multiple times. And the first case is Grand Safe Bicycle. And some products based on BLE implement by certain manufacturers have vulnerabilities. Attackers can renew the timestamp of expired commands to keep them valid and easily unlock smart U-locks. And this could lead to the thief of our means of transportation or from shops. First, I will introduce some BLE analyze bases. And first, capturing BLE data requires special hardware, which we can be done with NF dongle, and we will analyze with Wireshark. Secondly, it's necessary to understand GATT, and which is basis for BLE application development. And generally, a GATT server has multiple servers on it, and each service contains multiple characteristics. Usually, we directly operate on characteristics. So, what are some basic way of operation? First, the master device can send read and write requests to the slave device. Similarly, the slave device can also send data to the master, but the master needs to subscribe to the slave through notify or indicate. And usually, since the BLE protocol supports interaction with one side generating a random number and the other side challenging it, BLE authentication is difficult to simply replay the attack. But this vulnerability is very counterintuitive. So let we take a look at what's going on. This command comes from the unlock signal we captured. The 0150 command indicates unlocking, and it forms a field together with the timestamp, and it is signed with the key using HMAC SHA-1 calculation. And this green part is the signature used to ensure the field has not been tampered with. Okay, let's take a look at the normal unlock process of the lock. Our app generates a command using this current time, and the lock not only verts this command signature, but also checks the timestamp. If the timestamp differs greatly from the internal time of the lock, it will discard the command. If the difference is small, and it will successfully unlock. And analyzing to this point, the first thing I thought of was not a security issue, but unusability issue. What if my phone's time is not synchronized with the door lock's time? So I tried to change my phone's time, but the phone still successfully unlocked, just with a slight delay. After package capturing analyze, I know the reason. If the door lock timestamp is wrong, the phone will send an 0840 command to refresh the door lock timestamp, so that the timestamps of both sides become synchronized again. So the reply attacks are revived now. The attack method is very simple. first hijack the unlock command to make the app think the timestamp is synchronized and it is not synchronized, sorry. And then the app sends the refresh command and we capture the refresh command. Okay, finally, we just need to resend the refresh and the unlock command to refresh the door lock time and open it. So this is the demonstration. So the first step is the normal lock opening. And the second step, we capture the command. And the second step, we try to only replace the unlock command, but we fail. And finally, we open the lock by refreshing the timestamp. Okay, fine. Okay, so. Okay, moving on to the chapter 2. Now that we have looked at some of the issues with BLE application layer, let's dive deeper and discuss the security of BLE protocol itself. When shopping at a convenience store in China, the most common payment method is for the clerk to scan the payment code. And the vulnerability I'm going to introduce is an attack against BLE barcode scanners by directly attacking the BLE protocol to steal the payment credentials, then take the money and run. So this is the attack surface I analyzed. The user's payment code is a random number calculated use the user's root key in the TE. If we obtain this payment credential, we will deduce money using the mentor's privileges with the deductible amount set by us. And after analyzing the BLE communication of the barcode scanner, there is no application layer design at all, and completely relying on BLE link security. So what we need to do is hijack BLE. We only need to attack BLE itself. So for comparison, let's first understand some common radios. And conventional radios usually do not have frequency hopping or have very simple frequency hopping mechanism. For example, the Wi-Fi typically works on a fixed frequency bands, and car remote control key typically works on 433 or 315 megahertz bands. And NRF24 does frequency hopping, but the hopping sequence is predictable. And secondly, many radio protocols also lack link layer design. The lack of connection or interaction mechanism makes authentication design difficult. In addition, their links are insecure, and the channel can be occupied. In layman's terms, whoever speaks the loudest is heard. And the BLE protocols are different, and BLE design a complete link layer and can secure that BLE communication parts can complete interaction. And more importantly, BLE has one of the most complicated frequency hopping methods in the radios. We all know that using the NRF dongle to capture packages, it is impossible to directly capture the established BLE link. And first we need to capture the connect in the package to know the frequency hopping related information before we can track it. So this is a difficulty. This is a link layer data package form. Let's first look at the header definition. The channel select algorithm first, and the BLE has two algorithms, and the next two parameters indicate whether the device address is public or random, and the TX add indicates the initiator device, and the RX add indicates the advisor device. And the LL data is the most important part in the connection package, which defines the physical characteristic of BLE communication. Among them, the access address is used as an identifier for establishing link layer communication, and the CRC init value is used for subsequent CRC calculation. The interval is the connection interval, and we know the BLE hop frequency, and the actual frequency is not fixed. So how does BLE communicate? This parameter is, in layman's terms, defines how often BLE hops frequencies. And the timeout is a timeout tolerance. And wireless protocols need to set a timeout mechanism. Once the time is exceeded with a response, the connection is considered disconnected. So let's look at the parameters one by one. The access address can be obtained by sniffing over the air packages, and the CRC init can be obtained by acquiring empty packages and then performing inverse operations. And the channel map determines which frequency bands we use, so we must know it. The way to calculate the channel map is to listen on each possible frequency band about every 4 seconds. If there is the access address characteristic we are tracking, and we record it. In total, it takes 148 seconds to acquire the complete channel map. And the connection interval determines the interval between frequency hops, which is critical. To get this parameter, we first need to understand the channel selection algorithm a bit. Here I take channel selection algorithm 1 as an example. If the current frequency band is Fn, and the next frequency band is Fn plus 1, this is obtained by adding the hop parameter to Fn and take mode 37. And since the module operation is periodic and hopping 37 times will definitely return to the original frequency band. So we just need to find a suitable channel, then listen for the interval between receiving two data packages and divide it by 37. And this way we can get the connection interval. This is the magic of mathematics. And obtaining the hop parameter is very simple because the range is small and about 5 to 16. We can obtain it through brute force. And finally, we are able to track the BLE hopping, and we need a method to hijack it. This mechanism is called supervision timeout, and we interface with the data returned by the slave repeatedly. After several times, the master will think the slave are disappeared. So the master actively sends a terminal in to disconnect this link. At this point, the hacker can take advance of the opportunities and seize control. So this is our demo video. So first we hijacked the BLE hopping information. Then we hijacked the BLE barcode scanner. And at this moment, we can see that, okay. We have GATT. We have GATT the things we want. Yeah. Okay. Okay. In the third part, I will introduce BLE controller relay. And the relay attack are a security risk caused by the modern killer's entry system. Before 2016, some BLE-based relay tools like GATT attack have been publicly disclosed, which perform attacks by emulating the gap layer in the BLE protocol stack. And relay attackers can use multiple relay devices to form signals from legitimate initiator to the target device by passing physical distance restrictions. And in fact, defending against the common gap layer relay attack is easy. This is because in the BLE product stack, conventional BLE relay tools mainly perform relay attack against the gap layer in the host layer. However, the BLE protocol also includes the SMP, aka Security Manager Protocol, and this layer for encrypting BLE communication. As long as device adopt the link layer encryption feature built into BLE, and it can effectively prevent a relay attack. So naturally, our attack focus so naturally our attack focus on the from the host to controller. Can we try to perform relay attacks against the controller? And the BLE is a radio communication after all. Referencing RF relay solution to directly amplify the signal sounds feasible. But is it really viable? And stay calm and hear me out on this scenario below. Then you will be able to draw conclusions. And the right figure shows a connection event of a BLE device. In this event, the initial communication occurs on channel 8, and the central device sends information to the peripheral device and waits for a response within the conventional connection interval time frame. After receiving the request, the peripheral device returns a response package, and through the same channel, after the communication is completed successfully, the communication hops to channel 25 and continues the same operations, and successfully completing the next communication. So, and the next figure shows another connection event of a BLE device. This time, we relay the BLE signals over TCP IP. The initial communication occurs on channel 8. The central device sends information to the peripheral device and waits for a response due to the latency of TCP IP. When the device response returns, the central device has already hopped to channel 25, waiting for the next communication. Since the timeout events exceeded the limit, the central device thinks the peripheral device is disconnected and sends a terminal command, causing the communication to fail. And this is why BLE cannot be simply relayed by amplifying the signal. And because for the physical layer relay, we need to keep the hopping on both devices. So, how can we relay? Actually, the answer is in the question itself. The entire data structure represents everything BLE transmit on the physical channel, but the most important one is the link layer PDU, and which carries all host layer communication data for BLE, and the other parameters are for maintaining the link. So we only need to deliver the link layer PDU, discarding access address and CSE init. So there are a few more keys. First, discard the access address parameters in the data package. Separate link connection established on each side, and the device negotiate connection parameters separately, using empty package to fill each connection interval, and fill with the interaction data inter if there is any. Each connection event is no longer affected by TCP/IP latency, avoiding supervision timeout caused by no response. And after establishing the connection with empty packages, let device 1 and device 2 chat with each other, sending link layer control PDUs or link layer data PDUs. We are only responsible for relaying these link layer PDUs. So this is BLE link layer relay. Through packages capturing tests, I found device 1 and device 2 exchanging PDUs. To my surprise, I discovered the ATT layer. The ATT layer data was transmitted normally. So, and some vendors switched to Phi2 channels after link encryption to evade snooping or relaying. And specifically, once a channel is encrypted, the link layer data package will be encrypted, causing us be unable to parse their content. And the link layer control contains important data about channel state and hopping info, so we can't actually track channel changes. And to prevent losing track due to the hopping, we proactively switch to the Phi2 channel before encryption. By adopting this strategy, the Phi2 channel is fixed before the link encryption, thus avoiding the impact of hopping on tracking. And this is a demonstration video of our attack on a certain car mode. So first, the owner locks the car. And the owner is far away from the car. And the first attack come next to the owner. And the second attacker come to the car and success open the car. And we can drive the car away. Okay. Okay, thank you.
Good morning, everyone. Thanks to my partner for introduce our research to you. I'm Dalin from Xiaomi. Next, I will introduce tools and BLE security defense for you. This picture is an NXP method for defense the BLE relay. First of all, talk you about BLE link layer relay. As we know, relay is expand the signal distance. The follow is NXP anti-Bluetooth relay method. Whether it's effective against traditional relay attacks, there is no doubt that the method has reduced the transmission time of inactive data over the air to 3.6 microseconds, which has made traditional relay unable to complete the data exchange. However, BLE link layer relay is different from the traditional mode in that both partner establish a complete link layer connection. So each data transfer is not affected by the microsecond level, but also consider the network delay, which is the delay of request and response, not the timeout of each over the data transmission. Therefore, this method can't defend against such link layer relay attacks. Next, this figure shows the packet structures we built, but don't consider about channel map, access address, CRC init, and so on. We relay useful PDO data and classify it, such as link layer control, link layer data, and discuss empty packets. First of all, okay, sorry. The difficulties in the research process are as follows. First, data encryption at the link layer and the configuration parameters and at the link layer are changed in the interactive process. The most obvious difference is that the physical layer transfer relay parameter changes from 1 megabits per second to 2 megabits per second during data interaction. Second, the MAC address of Apple device make it often impossible to find a valid broadcast data during the test. Third, encrypt data at the link layer and configure the more data function for packet transmission. This made it difficult for us to resume the packets. First, other methods such as auxiliary connection, whitelist adjustment, and require user attention to complete the connection. Okay, let's start our tools, which contain is following features. It contains link layer relay, controller, hijack, and sniff and fake the packets and identify the non-standard UUID service of GATT. The advantage of these tools is that the intelligent the multiple BLE security test tools, and it's a mobile terminal device that supports the battery power supply and touch screen operation. The right picture shows the interface and the functions of the tools. Alright. Let's continue with the hardware and the software architecture background of the tools. Due to the long hardware production cycles, we use the modular hardware to combine the tools. It contains Raspberry Pi 4 and NF51822 dongle and TI-CC2652 model and LTE USB dongle for network. The software, we use the BLE model with modified protocol stack firmware to interact with a PC with Python environment. The software use the BLE models with modified protocol stack firmware and include Qt, Python, and Sniff LE and the controller hijack. Okay, let's look at the video of the tools. this testing the BLE relay. This client tools. The random has server tools. We transmit the data from the master and the slave. We can see that transmitted by the TCP sockets. Okay. All right. Let's talk about some of the difference in the tools development process. The main difficulty of the tools is to combine the hardware's platform, and adapt the system to the system, and the performance of the hardware, network environment configuration, and network delay optimization also need to be done. Let's take a look at the application sensories of the tool. BLE is known to apply to large numbers of IoT devices, and the tools can assist manufacturers, engineers to conduct more ultimately BLE security evaluation and test. As the cars become more and more intelligent, virtual BLE keys, car BLE equipment, and security threat test case analysis. In the future, we want to make the tools more and more intelligent, and as mentioned above, this tool uses many models. We will hope to integrate them into one main board. Extend the detections items of BLE, such as adding link layer fuzzing test, GATT service fuzzing test, and the historical CVEs inspection test. This expects that this year we will open the source of the softwares and hardware of the tools on the GitHub, and hope that you can make suggestions and add new functions. The next is BLE security defense. BLE layer encryption, update link layer transmission parameters can effectively reduce the possibility of being sniffed. More data is similar to TCP fragmentation. It tells you that there's still data package to be transmitted. Please continue to open the window. A connection event connects multiple data package interruption. So based on link layer encryption configure, more data is effective. In the field of the car keys, multiple Bluetooth models are used to assist in making connection devices, but all measures are reduce the security risks. It's still possible to complete the link layer attacks by remodifying the matching the protocol stack firmware. The defense measures at the GATT layer as follow. SMP handles security between BLE devices, including authentication, encryption, and the key management. The main goals of SMP is to security communication between BLE device and provide protection against the threats such as dropping and tamping and sniffing and man-in-meat. Important service data is encrypted before encrypted transmission via BLE. Strictly control the read and write permission of UID also in need. Okay, thank you. That's all for my speech. Thank you, everyone.
Thank you. Any quick questions before we move to the next session?
Hello. Thank you so much for your presentation. Just a quick question. You say that you will publish your tooling, is correct? Did you plan to open source it or?
Yeah.
Okay.
We will open the source on GitHub this year.
This year.
We will optimization some functions because just like BLE link layer fuzzing and GATT UUID service fuzzing and so on.
You mentioned fuzzing too, so another question, sorry. Did you start to play with the fuzzing on BLE or some Bluetooth stack? So did you already get an idea? For example, did you start to fuzz advertising or any kind of things?
Sorry, I can't.
I just would like to know if you already start to fuzz.
Yeah.
And did you get already something ready that you plan to open source or you plan to fuzz?
Yeah, we will open the source first. As the staff, my company is allowed.
Okay.
Yeah.
Thank you again.